Hey everyone, Professor Michael Scanlan here. I have a question for you. What color is that? It's kind of clear. Maybe a grayish, bluish tint to it. Is that the color it always is, though? Color is a little bit tricky to define sometimes. Today we're talking about fluorescence. Now, fluorescence is an interesting process, right? Let's say you go somewhere where there's a black light and maybe you have some fuzzies on your shirt you didn't quite catch with the lint roller, and then everybody knows you missed a patch of fuzzies with the lint roller because those little fuzzies just kind of pop out, right, whenever they're under a black light. Well, that black light is emitting ultraviolet light. Now, sometimes called UV. Whenever it encounters a material, sometimes that material really pops and really glows. That's called fluorescence. Think of fluorescent lights, okay? So, do all materials do that? No, they don't. Okay, so what's the difference? Why do some materials respond to UV radiation, some don't? It's got to do with the electrons, okay? So whenever ultraviolet light, UV radiation, same thing, hits an atom, say, we'll just pretend we have one atom, that light is just energy, and the electron could absorb that energy. When it absorbs that energy, it's going to have more energy than it did before, right? So if it's at the right configuration, right, if the electron is at the right spot, and that depends on the material. Different materials are going to have different electron configurations. If you got an electron at just the right spot, right, a material able to handle it or able to hold it, then that UV radiation coming in, the electron is going to absorb it and kind of jump up. And it's going to jump back down. When it jumps back down, it gives off the energy. Now, if it just gave off the same energy that it absorbed, it would just emit ultraviolet light and we still wouldn't be able to see it. But what happens in fluorescent materials is it tends to take its time jumping down, or it takes steps jumping down. So let's say that it absorbs 10 units of energy. I'm just pulling numbers out of thin air now. The electron jumps up. Instead of just releasing all 10 at one time, it might do 3, then 7. Well, that smaller subset, or that smaller set of energy, that smaller amount of energy, might actually fall in our visible range. Ultraviolet is too energetic, it's too far out of our visible range. But when the electrons jump down, they might jump down and release increments of energy that do hit our visible range, and so we'd be able to see it. And so what would we see? We would see this material actually giving off light, fluorescing. Okay, fluorescent lights that are on top of me right now work off of this principle. They're filled with mercury vapor, and when you turn them on, it ionizes the mercury vapor, and that mercury vapor releases some bluish, violetish light, and it releases some ultraviolet light. The electrons, whenever it becomes ionized, it becomes a plasma. The electrons have a lot of energy, and they can jump down and give that energy off in the form of light. So in these fluorescent tubes, you'll have this thin powder coating, okay? And what that does is that actually fluoresces whenever the ultraviolet light hits it from the mercury, and it makes it glow whitish, okay? And so that's why fluorescent lights work. So today we're going to look at materials that fluoresce. Now that we know why they fluoresce, it's because of the electrons. Why don't some other ones, fluoresce? Why do only a few? It's the electrons. The ones that don't fluoresce have electron structures that are not hospitable to UV radiation. In other words, the electrons can't make the right jump to absorb that radiation, so the radiation they just kind of ignore it. All right. We're going to look at some pretty cool things, in my opinion, that fluoresce, and a little bit of ultraviolet radiation, maybe something that you didn't know about it. Let me show you my setup before we get into all that. Okay, so I have a box. Wow, you have a box, cool. It's a box that has a black light in it, has an ultraviolet light in it, and it's got 2 different wavelengths of UV radiation because, as you'll see, not everything responds to the same wavelength. This is a fluorescence analysis cabinet. I don't know if you can read it on the screen, but it's down there. It's a fluorescence analysis cabinet. And it's got a window here that you can look in, and the box is kind of sealed off. It's got these little flaps to try to keep light out. Now, I'm going to bring the camera and put it into the viewfinder here, and then we're going to take a look and see what we have inside. Here we have some minerals in our box. Okay. This is the crystal we started with. I said, what is the color of this? And I mean, you can kind of see it's kind of clearish, maybe a small little twinge of gray or blue in there. I've also got a chemical compound known as rhodamine 6G. And I want you to take a look at it and see that I'm knocking everything. It's kind of a dark brownish reddish color. Okay. What we're going to do next is turn off, oh, and I've got a piece of tape in here too, is turn off the white light and turn on long wave ultraviolet. Here is that crystal. Now notice it's not so clear anymore, is it? It's fluorescing. This is fluorite. It's actually named for its fluorescent properties. Here's another mineral that you can see. It's got some inclusions here that are fluorescing. This one just looked like a big white rock. But now it's got these, sorry, this box is so small. It's got these red fluorescent patches in it. Okay. This one just looks like a gray rock until you look at it under ultraviolet and you see that things inside, not just the crystal itself, but the mineral inclusions or the chemical impurities inside the crystal are also glowing. Now that yellow is coming from the tape. It's not coming from the mineral itself. It's actually showing up through the tape. Let's look at short wave, a different type of ultraviolet radiation. You see our fluorite doesn't fluoresce in the same way, but check out what's happened to our rhodamine. It's now glowing red. Again, we can look at this one and see that there are things glowing in the crystal itself. So that's pretty cool. Let's take one more look at these in white light. This was that one that we saw that had stuff glowing inside of it. It's really tough to tell that there's stuff in there now, isn't it? This is the one that was glowing reddish. This one was black, except for this little top part right here. And here's our original little piece of fluorite. So fluorescence occurs naturally. It's not just something that happens in artificial materials like fabrics. And I want to show you something with this particular piece of tape here. So I've scooted our tape over a little bit. This is just yellow gaffer's tape. It does fluoresce in both long and short wave. Okay, so it does give off a fluorescent light in those wavelengths. But what I want to showcase is its reaction to glass. So I have a piece of glass here, and I'm going to place it over this tape. Let's look at long wave. See how it's pretty much fluorescing no matter what. Let's look at short wave for comparison. Now hopefully you can see the glass looks a little bit different, and the middle part here isn't shining as much as it is here and here. Let's look at long wave again. See, the glass just looks like glass. Short wave, the glass looks different. And I'm getting shining here and here. I can see through the glass, but I'm not getting the same fluorescence I was before. What's happening? The glass is opaque to this ultraviolet light. In other words, this ultraviolet light can't really pass through the glass. So I'm not getting very much fluorescence at all through here. Think about this for a summer day, or any day really, but summer day. You're standing outside, you can get a sunburn, right? You go stand next to a window on the inside, same day, you're just inside next to a window, you're looking at the same scenery, it's the same sun, but you're not at risk for a sunburn. Why? Glass is opaque to some forms of ultraviolet light, and that's what actually causes sunburn, ultraviolet light. All right, I hope you've enjoyed this quick little peek into fluorescence. I'll see you in the next one.